Today, we're going to nerd out with the law of large numbers and discover it by writing some Python code to find the law of large numbers and see if it really works out. So the law of large numbers, as a reminder, tells us that the average result will tend towards the expected value the more samples that we get. So what this means is, for puzzle number 1, we want to write a simple simulation that rolls 2 6-sided dice and records the sum of those rolls. So let's go ahead and do this simulation in Python real quick by saying data is equal to square brackets for I in range. I'm going to go ahead and simulate 10,000 times. And then I'm going to say the result is equal to, I just want the sum of the 2 dice. I could do the dice individually, but I'm going to do random.rand int 1, 6 plus random.rand int 1, 6. So this rolls 1 die, rolls 2 dice, does all in the same line of code in Python, and then sums the result together. So we get the result. We need to accumulate the result. So we can say D is equal to curly brace result in quotes, colon result. And then we have data.append of the D. And then we finally say df is equal to pd.dataframe of our data. And here, of course, we're using the pandas library and the random library. So we need to both import pandas as PD and import random to use the 2 libraries that Python's providing for us.
And I went ahead and ran the code, no errors.
And if you type df, what do we get?
df, I get a data frame with 10,000 rows, 1 column called result. And it looks like I have 8, 5, 7, 8, 3,
awesome.
8, 7, 11. A lot of 8s.
Oh, interesting. That's a pretty frequent roll of rolling 2 die, though. So one really nice thing, as we want to discover the law of large numbers, we want to understand averages. So Python provides something called a cumulative sum function. So we can find what the cumulative sum of a particular value is. So we want to calculate the cumulative sum of a particular column. So our column we have, if we look at our data frame, right now we have our data frame. Then we have a dice total, which we actually call this total result in our code we wrote up here. So I'm going to make sure it's consistent here in this table. And then I want to know the cumulative sum of result. So here what I'm going to use is I'm going to use a new function to create a new column. So what I'm going to do is I'm going to do df at the cumulative sum, which we abbreviate as sum for cumulative sum. And that's going to be equal to the cumulative sum function. So that's going to be equal to df of result dot cumulative sum. So I'm adding a new column called cumulative sum, and that's going to be equal to df at result dot cumulative sum, or cum sum. So if I run this line of code should do nothing.
Did nothing.
But if I do df, what do you see in the cumulative sum column?
Ooh, so I see a new column, cumulative sum, that is increasing.
That is increasing, yes. So if I look at this data I have right here, so this sample data, so Carly, actually, let's do it with real data. Like, why even use sample data?
Why
We're data scientists.
Yeah, you love real data. Wow.
Give me the first 7 values.
So I have 8, 5, 7, 8, 3. And then it does the dot, dot, dot.
Ah, okay, yeah, we only have,
so
we could do, so let's even get, so one way to do that is if we want to look at just the first 7 values, let's do df.head 7.
Of course. And okay, so we have 8, 5, 7, 8, 3, 5, 6.
5, 6. Oh, interesting. We never got a 10, 11, or 12. We kind of had some low rolls.
Yeah.
Then the cumulative sum column, I'm guessing the first row is an 8.
8.
Second row should be 13.
Yep.
Then 20.
Yep.
Then 28.
Yep.
Then 31.
Yes.
Then 36.
Yep.
And then 42.
You're psychic.
So all I did was I looked at what the sum was of everything beforehand. So the cumulative sum simply adds these two values together. So it's a really easy thing to calculate. And now the average function is going to be one of the most complicated functions we have yet, because we want to know basically the cumulative average. Unfortunately, there is no cumulative average function.
Got it.
So for the cumulative average, we're going to have to take the cumulative sum and divide it by the current row we're on.
Right.
So you have a bold number way on the left-hand side, right?
The index, yes.
The index value, yes. So to get the average, we can write a new line of Python that says our df at, we're going to call this the average, AVG, is going to be equal to, well, it's going to be equal to a df at the cumulative sum divided by, and in parentheses, we're going to do df.index plus 1. Because what I want to do is on this first row, I want to do 8 divided by 1. So I don't want to do 8 divided by 0 because that doesn't exist. Second row, I want to do 13 divided by 2 to get the average. Third row, 20 divided by 3. So if you run this code, you should get a new column, a third column called AVG.
Yes.
And is the first one 8?
Yep.
And is the second one, let's see, 13 divided by 2 is going to be 7.5?
6.5.
6.5. 20 divided by 3 is slightly less than 7.
6.67.
And then the third one is going to be 28 divided by 4, so that's
7.
7. And then 31 divided by 5
is 6.2.
So we see we have the cumulative average, and we see that as we get big numbers like 8, our average goes up. As we get small numbers like 3, our average went from 7 to 6.2.
Right.
And the law of large numbers tells us as we take more samples, this average should get closer and closer to the expected value. So I want to see if this is true or not.
Let's test it out.
So one thing we can do is we can look at just a subset of the data. So if you do df and then do a square bracket, and you insert numbers in that square bracket, you're asking Python to give you a range of rows. So if you do df at 0:10 inside the square brackets, what do you see?
I see the first 10 rows.
So this displays only the first 10 rows. And if you change that df to df 0:100, what do you see?
First 100 rows.
First 100 rows. So this range notation is really valuable because we can ask Python to just give us the first 10 rows or the first 100 rows or some other range within that range. So it's the starting number and one past the last number. So, or sorry, the starting index and one past the last starting index.
Right.
So 0:10 gives us 10 total numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So I'm actually interested in creating a plot of this data. So I want to see a line graph of where this average goes. I want to understand how this average works to see if we're actually getting closer to the expected value.
Right.
So what I want to do is I want to say df, and I want to just select the first 10 rows. So df 0:10, and then I only want to look at the average column. And then let's do .plot.line, open close parentheses. So this is the first 10 rows, only look in the average column, and I'm going to plot a line chart with this data. And what do we get?
So we get a line graph where the x-axis goes from 0 to about 9. It kind of goes down, then up, then down, then up again.
It's all over the place.
Yeah, it doesn't really tell us much.
So let's go ahead and change this. So what's the range of that graph?
So the range, the y-axis actually goes from about 6 to 8.
So about 6 to 8, so quite a wide range.
Yes.
So now let's go and look at df of 0 to 100. So let's change almost the exact same line, but instead of 0 to 10, let's add an extra 0 there.
Interesting.
So this graph looks different now, right?
Yeah.
So we see that the original graph is still there, now kind of in the kind of left-hand side of the graph, but we're kind of normalizing to a more even value.
Yeah.
So, and what's kind of the range of the right half of the graph?
The right half of the graph is kind of from like 6.25 to 6.75.
So 6.25 to 6.75.
Yeah.
of the right-hand side of the graph. Interesting. All right, so that's just 100 results. So as we get more and more results, we did a simulation of 10,000 results. So let's look at the first 1,000 rows now.
Ooh, okay. So I'm changing 100 to 1,000. Wow. And it is really, it kind of levels off right at 7.
So yeah, if we look at what is the range of the right half of the graph, what do we see, Carly?
It's like 6.9 to 7.1.
6.9 to 7.1. So we're seeing as we're taking more and more samples, you see that line getting closer and closer and being more and more consistent to that expected value.
Yeah, which we know is 7.
And let's go crazy and go all the way to 10,000, every single result we've got.
Okay, 10,000. Wow, and it forms almost a straight line right at 7.
So at this point, now that we're almost at that entire point, we're almost at the exactly expected value. The range of the right-hand side of the graph, I'd say, is what, like 6.98 to like
Yeah.
7.02.
Yep, pretty much.
That as we get more and more samples, the range that we're getting of the points that are in the right side of the graph, the last half the points we're looking at, is getting narrower and narrower
Getting
and narrower.
smaller.
So let's see. So some analysis on this data. I mean, we kind of looked at this, but Carly, if we just think about the statistics, what's the actual expected value we're expected to get when we roll 2 die and calculate the sum?
So the expected value is 7. So the most common outcome, if we look at the sample space of rolling 2 dice, the most common sum is 7.
So, and we saw that graph as we added more and more samples really went closer and closer and closer towards 7. Towards the end, it basically being a straight line at 7. We're not
Yeah.
changing the average at all. The more samples we take, we really are seeing it come closer and closer to the expected value. So what happens to the cumulative average as we show more and more simulations? It tends towards the expected value. And as we do simulations for really simple things like just 2 dice, you're going to see it's going to tend towards the expected value very, very quickly. There are going to be some things that it's going to take many, many, many more samples. It could be millions of samples before you see it tending towards the expected value.
Yeah.
So it's always going to tend towards expected value. The number of samples you need matters mostly on the complexity and the variance of the underlying data. So, but we know that as we get more samples, we're going to get more accuracy in our result. So when we do simulation, we're always going to try and simulate lots and lots of data so we can get a really accurate result. And this mathematical law, the law of large numbers, really lets us know mathematically that what we're doing by adding more and more simulations really does gets the average closer and closer to that actual result.
And we know this is going to happen every time since it's a law.